Hi everyone. So first of all, let me know, is audio and video everything clear here? Yes. So first of all, let me know whether audio and video everything clear. Yes here. So if audio and video everything clear, then we'll start the session here. Yes. Okay. Anand, this session you told it's a problem session. We'll solve problems also here. What is there? Okay. Right. Okay, dear. So we'll start the lecture here. I hope audio and video everything is clear. So we'll start the lecture. So the subject is electromagnetics. So the subject is electromagnetics. Okay. Okay. So up till now here, what we have studied here up till now. So up till now we have seen basics of vectors. So we have studied basics of vectors, right? Next we have studied coordinate systems. We have studied coordinate systems. Okay. So after that, basics of vectors, coordinate systems, and then after that I have started with vector differential operator. Vector differential operator. Okay. So in vector differential operator, we have studied some topics here. What are those topics here? What are the topics that we have studied in vector differential operator? So we have studied gradient. We have studied the operation, vector operation, that is gradient, right? And then we have studied about flux, and then we have studied about divergence, right? And then we have studied about circulation, and then we have studied curl, right? So these are the topics we have covered up till now here. So what are the topics we have covered? So we have covered basics of vectors, and we have covered coordinate systems, and we have covered vector differential operator. So in vector differential operator we have studied gradient, and then we have studied flux, and we have studied divergence, and then we have studied circulation, and then after that we have studied curl. Okay. So these are the topics we have covered up till now, right? Okay. Okay, so we have studied up to curl here. We have studied up to curl, yes or no? And we have seen that whenever the divergence of vector field, is equal to 0, then f bar is said to be what here? F bar is said to be divergence-less or solenoidal. Divergence-less or solenoidal, right? Okay. Next we have studied a divergence theorem also here. What is divergence theorem here? So closed surface integral f bar dot dA bar is equal to what? Is equal to triple integral divergence of f bar into dV. So this is nothing but divergence theorem. Okay. Next right. So next we have seen that curl of any vector field So curl of any vector field, if curl of any vector field is equal to 0, so then f bar is said to be what here? F bar is said to be irrotational. F bar is said to be irrotational or curl free or conservative right. Okay, so these are the things we have covered here. These are the things we have covered. And also we have seen circulation of vector field. Yes or no? How to represent the circulation of vector field around any closed loops. All those things we have seen here. Okay. Okay. Yeah. So now I will just briefly explain Stokes theorem here. I will just briefly explain Stokes theorem. See here. So here I have explained divergence theorem, right? So this is divergence theorem. So now I will explain simply Stokes theorem here. So I will explain in a brief manner here. See here. See, we know how to represent the circulation of the vector field around any closed loop. How we can represent here circulation of vector field around any closed loop? How we can represent? We can represent it as closed loop integral f bar dot what? F bar dot dl bar. So this represents what here? This represents circulation of vector field. Circulation of vector field around any closed loop. Around any closed loop. Right. Okay. So we know this one here. We know this expression. This expression is nothing but circulation of vector field around any closed loop. Let us consider this as 1 here. Let us consider this as 1. Okay. Now see here. Let us assume here some vector field is present in this region here. Let us assume some vector field is present in this region. Now I want to determine how much of this vector field is lying or aligned or circulating around the given closed loop. See, I am not drawing the vector field here. Just assume some vector field is present in this region. Now I want to determine how much of this vector field is circulating around this closed loop. I want to determine how much of this vector field is circulating around this closed loop here. Some vector field is present. Now I want to determine how much of that vector field is aligned around this closed loop or circulating around this closed loop. See here, if suppose some vector field is circulating around this closed loop, means inside this closed loop there must be a source of that circulating field or not? Yes or no here? If some field is circulating around this closed loop, means inside this closed loop there must be what? There must be a source of that circulating field. Now if you observe this loop is enclosing this surface area. Right? Okay. So that means there must be some source. Within this surface area. That is bounded by this loop. Okay, and that source is the cause for what? That source is the cause for circulating field around this closed loop. Right? Okay. Okay here. So what I am saying here is some field is present here. Now I want to determine how much of the field is circulating around this closed loop. If any field is circulating around this closed loop, means inside that closed loop there must be a source of that circulating field. Right? So if you consider this closed loop, it is enclosing this surface area. Okay, so now let us assume throughout this surface area some source is distributed here. Right? Now I can represent that source. As source distribution as many sources here. Many sources that are distributed throughout this surface. Okay, so I can represent that source distribution as what here? Many sources that are distributed throughout this surface. In this manner I can represent that source distribution. Okay, so these are the sources of what here? Each and every point source is a source of what? Is a source of the circulating field. Right? Okay, so now So now what I am doing here is I'll try to determine the circulation of the field, circulation of the vector field about this point here. So I'll try to determine the circulation of the vector field around this closed, about this point. I am trying to determine the circulation of the field about this point, right? Okay. So let us assume the field is circulating about this point in this manner. Now here also I am having source. So this source is also producing some circulating field. So let us assume it is producing the circulating field about this point. So this is the field that is circulating about this point. So in the same manner here the field is circulating about this point. The field is circulating about this point. Here also the field is circulating about this point. The field is circulating about this point, right? Okay. Now here also the field is circulating about this point. Now here also the field is circulating about this point. So like this here. So like this I am trying to determine how much of the field is circulating about the given point source, right? So right. Okay. So here here this is the circulating field about this source point. This is the circulating field about this source point. This is the circulating field about this source point, and so on and so on, right? Okay. So now if I add up this circulation about this point and about this point here, if I add up the circulation about this point and about this point, if I add up the circulation about this point and about this point, what I am going to get here? So whenever you are adding the circulation about this point and this point, what you are going to get? See here, whenever you are determining the circulation along this line here, whenever you are determining the circulation along this line, it is pointing in which direction? In this direction. So for this one, the circulation of the field along this line is pointing in this direction. So if whenever you are adding these two circulations, these two will get what? These two will get cancelled. And if you observe here you are determining the circulation along this line, and with respect to this source here, with respect to this source, the circulation of the field is pointing along this direction. So whenever you are adding up these two, these two will get what? Cancel. So similarly, if you add up these two will get cancel. If you add up these two will get cancel. Yes or no? So whenever you add up these two circulations, these two will get cancelled, and here these two will get cancelled, 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 so and so on here, and so on. So what is the conclusion is, internal circulations here, wherever you are determining, the internal circulations will get what? Will get cancelled. Yes or no? So here these two will get cancelled, these two, everything will get cancelled. Okay, internally all the circulations will get what? Will get cancelled. So finally what is left out here? So the field circulating along this line, and here the field is circulating along this line. Yes or no? So whenever you are adding up these two, so this is pointing in this direction, this is also pointing in the same direction. So these two will get what? These two will get added up. So in the same manner, whenever you add the circulations along this direction, then what will happen? Okay, so this one and this one and this one all will get what? See here. So this will get what? This will get added up, and here this one all are pointing in the same direction. So whenever you add the circulations about each and every point, this will get added up, this will get added up, and here this will get added up, and here this will get added up, right? Okay, so internally everywhere it will get cancelled, So finally what you are getting here? You are getting the circulation around this closed loop or not? Yes or no? Finally you are getting the circulation of the field around this closed loop. Yes or no? So what we have done here, you have considered the source distribution as many point sources, and each and every point source is producing some circulating field, yes or no? So now if you add up the circulations, at each and every point here, at each and every point throughout this surface, what we are getting, internally everywhere the circulations will get cancelled, and we are going to get what? The circulation of the field only on the outer loop, yes or no? Only on the outer loop, right? So that means what here? If you add up the circulations about each and every point throughout this surface, finally you are going to get what? You are going to get the circulation of the field around this closed loop, yes or no? So circulation about each and every point means what here? Circulation about a point is nothing but what? Curl, yes or no? So that means if you add up the curls here, at each and every point throughout this surface, then what you are going to get? Finally you are going to get the circulation of the field around this closed loop, yes or no? So what is the other way to represent what? What is the other way to represent the circulation of the field around any closed loop here? If you add up the curls at each and every point throughout this surface, then you are going to get the circulation of the field around this closed loop, right? Okay, so if you consider a small differential area, and if you add up the curls over that small differential area, I can represent that as del cross f bar dA bar. So if you add up the curls over a small differential area dA bar, then I can represent in this manner. Now if you add up all the curls, at each and every point throughout this surface here, then what you have to do? You have to integrate throughout this surface. So this is going to give you what here? This is nothing but what? If you add up the curls throughout this surface area, at each and every point throughout this surface area, finally you are going to get what? You are going to get the circulation of the vector field around the closed loop, yes or no? So this is, let us say this is expression 2 and this is expression 1. So both expression 1 and expression 2 will represent what here? Will represent the same, yes or no? So therefore I can represent circulation of the vector field around any closed loop is equal to what here? Is equal to double integral del cross f bar dot what? Dot dA bar. So this is called as what here? This is called as Stokes theorem. Yes or no? Okay, so this is called as Stokes theorem. See, if you compare with the divergence theorem here, in divergence theorem what we have done? Closed surface integral f bar dot dA bar is equal to what? Is equal to triple integral divergence of f bar into dV. So this is nothing but divergence theorem, yes or no? So this is nothing but divergence theorem, right? So here what we have done here, if you want to determine the flux that is leaving any closed surface, that is equivalent to what? That is equivalent to summation of all the divergences at each and every point throughout the volume, yes or no? Here this closed surface is going to enclose a volume, yes or no? So within that volume you must have what? You must have the source of this field here, So if you add up the divergences throughout the volume here, that is enclosed by this closed surface, then you are going to get what? You are going to get the flux that is leaving the closed surface. We have already discussed this one here, divergence theorem, yes or no? Here also in the same manner here, if you want to determine the circulation of the vector field around any closed loop, then what you have to do here? You have to add up the curls, throughout the surface at each and every point throughout the surface. So if you add up the curls at each and every point throughout the surface, that is going to give you finally the circulation of the vector field around any closed loop, right? Okay, so This we call it as Stokes theorem, and this we call it as what here? Divergence theorem. See, the purpose of Stokes theorem and divergence theorem is what here? By using these theorems, the problems or mathematical calculation will get what here? Will get very much simplified. Yes or no? Okay. Okay, yeah. See, previously we have done some problems here, that is we have tried to determine the circulation of the vector field around any closed loop. Yes or no? We have tried to determine the circulation of vector field around any closed loop. So here what we have done? We have determined the integration of f bar dot dl bar along this line plus integral f bar dot dl bar along this line plus integral f bar dot dl bar along this line plus integral f bar dot dl bar along this line. So if you add up all this here, if you add up all this, you are going to get the circulation of the field around any closed loop. Okay, so how many times you have to do the integration here? We have to do the integration 4 times here, 4 times. Yes or no? So instead of this, if you know the vector field, then you can apply what? You can apply Stokes theorem. So circulation of vector field, if you want to determine circulation of vector field around any closed loop, you can use simply Stokes theorem here. So that means try to determine the curl of the vector field and integrate that throughout the surface area. So that then you are going to get the same result here. Same result. Okay. Okay, yeah. See, for example, we have done for f bar is equal to x ax cap plus y ay cap. For this, what we got here? For this, we got circulation of vector field. For this, we got. So we have determined for this one here. Do you remember this one? This is x-axis, y-axis. So we have considered a loop here. We have considered some closed loop. So this is 0, 0. This is 1, 0. This is 1, 1. This is 0, 1. So we try to determine the circulation of the vector field around this closed loop here. For this vector field, if f bar is equal to x ax cap plus y ay cap, then we try to determine the circulation of this vector field around this closed loop here. Yes or no? Okay, so there what we got here? Circulation of vector field around the closed loop, we got it as what? We got it as 0. So there we have determined the integral f bar dot dl along this loop, along this line, plus integral f bar dot dl bar along this line, plus integral f bar dot dl bar along this line, plus integral f bar dot dl bar along this line. So this much calculations we have done here. Okay, so instead of that, if you use Stokes theorem, so this can be represented as what here? This can be represented as double integral del cross f bar dot what? Dot dA bar. Now what is the curl of this function here? See, I have already told that whenever they have given the vector function, always represent the x component. So this is x component of field, and this is nothing but what? This is nothing but y component of field. Now if you observe x component of vector field, here f bar is equal to x component of vector field is a function of what? Is a function of only x. Yes or no? X component of vector field is a function of only x, and y component of vector field is a function of what? Is a function of only y. Yes or no? So that is fy of y ay cap. Right? Okay. Okay, yeah. So I have already told that whenever f bar, that is, if x component is a function of only x and y component is a function of only y, then curl of f bar will be equal to what here? Curl of f bar is equal to 0. Yes or no? Already we have done all these things here. Okay, so whenever you are having a vector field, in that if x component is a function of only x and y component is a function of only y, then curl of that vector field will be equal to what? Will be equal to 0. Right? Okay, so that means now you can easily tell the circulation of the vector field around any closed loop. Yes or no? So that is double integral del cross f bar dot dA bar will be equal to what? Will be equal to 0, because curl of this vector field is equal to 0. So within one step you can tell the answer for this question here, right? So there we have done the mathematical calculation, yes or no? We have determined integral f bar dot dl bar along this line, along this line, along this line, along this line, and we have added up all this, yes or no? Okay, so it is the mathematical calculations involved here is more when compared to this one, right? So here we can directly tell the answer here. So that is the purpose of what? That is the purpose of this Stokes theorem and divergence theorem. This is Stokes theorem and divergence theorem, right? Okay, so I hope it is crystal clear here. I hope it is crystal clear. Okay. So Anand, what's your doubt here? Small doubt, sir. All individual circulations are in anti-clockwise. Why I have taken like that means I have told that, see, I have told that some source is distributed, yes or no? Some source is distributed in this throughout this surface area. I am splitting that source into many point sources. Yes or no? So this is the same source here. Some source is distributed throughout this surface area. Now I have splitted that source into small point sources, and I have tried to determine the circulation about each and every point here, right? Okay, so if you add up all these circulations about each and every point, that is same as what? That is same as the circulation of vector field around any closed loop, right? Okay. So internally everywhere it will get cancelled. So what is left out here? Only on the circumference of the loop. Only the circumference of the loop will get added up. Yes or no? Internally everything will get cancelled. Right? Okay. So that's what I have told here. Right. Next. So okay here. So next we will see null identities. Next we will see null identities. So what are null identities here? See here. You can calculate gradient of any function here. You can calculate gradient of any scalar function, and if you do the curl here, curl of gradient of any scalar function here, curl of gradient of any scalar function is always equal to what? Is always equal to 0. So that means take any scalar function here, take any scalar function and try to determine its gradient, right? So once you determine the gradient, you are going to get some vector field. Yes or no? So for this vector field, if you try to determine curl here, then always you are going to get what? Always you are going to get 0. Okay, so curl of gradient of some scalar function, is always equal to what here? Is always equal to 0. So this is first null identity. So you are having two null identities here. Second one, divergence of curl of any vector field. Divergence of curl of any vector field is always equal to what? Is always equal to 0. Is always equal to 0. Is always equal to what? Is always equal to 0. Right? So these are the two null identities here. So that means you can take any vector function, and try to determine the curl of that vector function here. Take any vector function and try to determine the curl of that vector function. So then you are going to get some vector function here. So for that vector function, if you try to determine the divergence, always you are going to get what? You are going to get equal to 0. Always you are going to get equal to 0. Right? Okay. So, okay. Now see here. So now this gradient of f is going to result in a vector quantity. So let us assume that vector is a bar here. Let us assume that vector is a bar. So now I can represent this one. I can represent this one as curl of a bar. Curl of a bar is equal to what? Is equal to 0. So that means I can say a bar is what here? A bar is conservative. A bar is conservative. Yes or no? So where a bar is equal to what? Where a bar is equal to gradient of what? Gradient of f. Where a bar is equal to gradient of f. Okay. So here gradient of f results in some vector quantity. So that vector quantity I am representing with a bar. So curl of a bar will be equal to 0. So if curl of any vector field is equal to 0, then that vector field is said to be what? Then that vector field is said to be conservative. Yes or no? So here a bar is called as what here? A bar is nothing but conservative. So any conservative field here, any conservative field can be represented as what here? Can be represented as gradient of some scalar function or not? Yes or no here? So any conservative field can be represented as what? Can be represented as gradient of scalar function. Yes or no? Okay. Okay here. So so here make down a note here, note. So this note is very important here, note. Okay. So any conservative field can be represented as what here? Can be represented as gradient of what? Can be represented as gradient of some scalar field. Gradient of some scalar field. So that's what we can make the conclusion from this one here. Okay. So this is what we can make one conclusion from here, right? Next, if you observe this one here, now here this del cross f bar, I am representing with some b bar here. Okay. So if you do del cross f bar, you are going to get some vector function. That vector function I am representing with b bar. So now this expression I can write it as what here? Divergence of b bar is equal to what? Divergence of b bar is equal to 0. Divergence of b bar is equal to 0. So what do you mean by divergence of b bar is equal to 0 here? This implies b bar is what? This implies b bar is what? B bar is solenoidal. Yes or no? B bar is solenoidal or divergence-less. B bar is solenoidal or divergence-less. So where b bar is equal to what? Where b bar is equal to curl of what? Curl of f bar. So that means any solenoidal field here, you can represent it as what? Any solenoidal field can be represented as what? Curl of some vector field. Okay. Any solenoidal field can be represented as curl of some vector field, right? So you make a note here, any solenoidal field can be represented as what? Can be represented as curl of what? Curl of some vector field. Curl of some vector field. So these notes are very important here. These notes are very important. So any conservative field can be represented as what? Gradient of some scalar field, and any solenoidal field can be represented as what? Can be represented as curl of some vector field. So these are the conclusions. We have drawn from this null identities here. Yes or no? Okay. So I hope it is clear here. I hope it is crystal clear. Okay. Is this clear here? Yes. Okay. So I hope it is clear here, right? Okay. Okay. So now, so we have seen Stokes theorem and also we have seen this null identities. Now we will solve some problems here. We will solve some problems, right? Okay. So these are the problems that are given in GATE here. Okay. So these are the problems that have given in GATE. So very simple problem here. See here, they have given a bar is equal to cos x sin y ax cap plus sin x cos y ay cap, and they are asking simply magnitude of what? Magnitude of curl of a bar. They are asking magnitude of curl of what? Curl of a bar, right? Okay. So I hope you can do this one here. I hope you can do this one. So this is nothing but what? This is nothing but x component of a bar, and this is nothing but what? This is nothing but y component of a bar, y component of a bar. Okay. So try to determine curl of a bar here. Try to determine curl of a bar. So I said how to expand this curl of a bar. So how to expand this curl of a bar? Yes or no? So you can write directly here is equal to ax cap into what? So here you are having x. So dou by dou y minus what? Dou by dou z. So here integrate the z component of a bar and here y component of a bar, right? Plus ay cap into dou by dou z minus dou by dou x, here x component of a bar and here z component of a bar, plus az cap into dou by dou x minus dou by dou y, right? So here you have to differentiate the y component and here you have to differentiate the x component, right? Now if you observe here in this expression here, in this expression az is equal to what? Z component is not present, so z component is equal to 0. Now substitute here z component is equal to 0, so this term will go to 0, and here you are having y component, yes or no? But here this y component is a function of what? Here this y component is a function of x and y, so it is independent of z. So if you differentiate this y component with respect to z, you are going to get what? You are going to get 0, right? Yes or no? Here you are going to get 0. Dev Sharma. Okay, yeah. So next x component differentiate this with respect to z here. So take this x component and differentiate with respect to z. See, x component is also a function of what? Only x and y, right? So if you differentiate this with respect to z, you will get 0. Z component is 0, right? And here y component is a function of x and y. So what you are going to get here? So take y component, so this is y component, and differentiate this with respect to what? With respect to x. So what you are going to get here? Differentiation of sin x, yes or no? Differentiation of sin x is cos x. So you will get cos x into cos y minus of, take x component and differentiate it with respect to y. So take this x component and differentiate it with respect to y here. So what you are going to get? So cos x into cos y, yes or no? Yeah. So take x component and differentiate with respect to y, you will get cos x into cos y. So cos x into what? Cos x into cos y, right? So what you are going to get here? This is equal to what? This is equal to 0. So that means the magnitude of gradient of a bar, will be equal to what? Will be equal to 0. So that means what we can conclude here? A bar is what? A bar is nothing but conservative. Right? A bar is conservative or curl free or irrotational, right? Okay. So this is very simple problem here. They have given in GATE here. Okay. Okay, yeah, fine. Next here, next problem. See here, next problem. Okay, now see what they are asking here. They have given a vector, they have given some vector field here. P bar is equal to what? P bar is equal to x cube y ax cap minus x square y square ay cap minus x square yz az cap. You are having x cube y ax cap minus x square y square ay cap minus x square yz az cap. Then which one of the following? Then which one of the following statements? Which one of the following statements is true? Which one of the following statements is true? Okay, so what they have given here? P bar is solenoidal but not irrotational. P bar is irrotational but not solenoidal. P bar is neither solenoidal nor irrotational. P bar is both solenoidal and irrotational. So that means you have to determine here, whether divergence of P bar is equal to 0 or not equal to 0, and also you have to determine whether curl of P bar is equal to 0 or not equal to 0. Okay, so this is what you have to check here. This is what you have to check. So based upon this, we can say whether P bar is solenoidal or irrotational. So like that. We can tell whether it is solenoidal or irrotational, or it is both, or it is neither. So like that we can judge based upon what? Based upon this one. So you have to check these things here. Okay, so now what I have told here, whenever they have given the vector function, so first always write down the x component, y component and z component here. So here the x component I am representing with px. Right, so here y component, in y component I am including this minus also here. So this is y component, and minus x square yz is z component, right? Okay, see what I have told here, whenever you are calculating divergence, what I have told here. So whenever you are calculating divergence of vector field, what I have told, so take x component and differentiate with respect to x, and then take y component and differentiate with respect to y, and take z component and differentiate with respect to z, right? So now take x component here and differentiate with respect to x. What you are going to get? You are going to get 3x square y. Now take y component and differentiate with respect to y. So then what you are going to get? You are going to get minus 2 into x square y. Next, take z component and differentiate with respect to z. What you are going to get? Minus x square y. So what you are getting? 3x square minus 2x square minus x square is equal to what? Is equal to 0. So from here you can say P bar is what? P bar is solenoidal. Yes or no? We can easily conclude P bar is what? P bar is solenoidal, right? Okay, next you have to determine curl of P bar here. So I have told how to expand this curl of P bar. Yes or no? Okay, so this is equal to ax cap. You have to practice this one here. Okay, so dou by dou y minus dou by dou z. Now here you have to differentiate the z component, and here you have to differentiate the y component. Next, plus ay cap into dou by dou z minus what? Dou by dou x. Now here you have to write px and here pz. Next, plus az cap into what? Dou by dou x minus what? Dou by dou y. Okay, so here py and here px. Okay, so now see here. Okay, now if you observe here, here px, here we are having px is equal to what? Is equal to x cube y. Py is equal to what? Py is equal to minus x square y square minus x square y square pz is equal to what? Is equal to minus x square yz. Okay. Okay. Now if you observe, this px is a function of what? Px is a function of only x and y, and py is also a function of what? Py is also a function of only x and y. Only z component is a function of what? Is a function of x, y and z. Okay. See so if you observe here, so first one, see here, so here ax cap into, so take z component here, so this is z component, this is z component, and differentiate with respect to what? Differentiate with respect to y. Differentiate with respect to y. Now see here, I will tell you a trick here, I will tell you a trick, there is no need to do all these things. Okay. See here, see, if suppose we want to check whether this curl of p bar, is equal to 0 or what? Or not equal to 0. This is what we want to check. See, if curl of vector field is equal to 0 here, if curl of vector field is equal to 0, then what is the meaning of that? So this is the x component, yes or no? This is the x component, and this is the y component, and this is the z component. So for this curl to be equal to 0, this x component must go to what? This x component must go to 0, this y component must also go to what? 0, and this z component must also go to what? 0. So then only the curl of the vector field is equal to 0. If any one of this component is not equal to 0, then curl is not going to be equal to 0. Yes or no? Now what is the condition? What is the condition for this x component to become equal to 0 here? What is the condition for the x component to become equal to 0? So this dou pz by dou y must be equal to what? Dou py by dou z. Yes or no? So you have to check whether dou pz by dou y must be equal to what? Must be equal to dou py by dou z. So for curl of p, if curl of p is equal to 0, then this x component must be equal to 0, y component also equal to 0, z component must also be equal to 0. So when this will be equal to 0? If it is equal to 0, then dou pz by dou y must be equal to dou py by dou z. So we will check this condition here. If this condition is not satisfied, then I can directly tell del cross p bar is not equal to 0. Yes or no? If suppose this condition is satisfied, if suppose here dou pz by dou y equal to dou py by dou z, so if this condition is satisfied, then this x component will go to 0, then I will check for y component whether it is becoming equal to 0 or not. So if here also this condition is satisfied, then I will go for z component and I will try to check the condition, right? Okay. So if here itself, if x component here itself, if I got if this condition is not satisfied, then I can directly tell del cross p bar is not equal to 0, right? Okay. Now see here, so z component dou pz by dou y, what you are going to get here? Tell me. Dou pz by dou y. So differentiate this function with respect to y, you will get what? Minus x square into what? Minus x square into z, right? Now take this one. So y component py is equal to what? Minus x square y square. Now you are differentiating this with respect to z. Yes or no? So py is a function of only x and y. Now you are differentiating this with respect to z. So you are going to get what? 0. So that means on LHS side you got minus x square z, and on RHS side you got what? You got 0. So that means dou pz by dou y is not equal to what? Is not equal to dou py by dou z. So that means this component is not equal to 0. This component is not equal to 0. So that means what here? We can directly tell curl of p bar is not equal to what? Is not equal to 0. Is not equal to 0. Yes or no here? If suppose this condition is satisfied, then we check this condition here. Here we will check whether dou px by dou z is equal to dou pz by dou x or not. So if here also this condition is satisfied, then we will go for this one and we will check whether dou py by dou x is equal to dou px by dou y. So here also if it is becoming equal to 0, then only, if all the components will become equal to 0, then only the curl of the vector field will be equal to 0. If any one of the components is not equal to 0, then also the curl of vector field is not equal to 0, right? Okay. Okay here. So just within the first component itself, by checking only the first component itself, we have concluded that curl of p bar is not equal to what? Is not equal to 0. See, always remember here, always you can make a note here, you can make a note here, you can make a note here. So if curl of f bar is equal to ax cap into dou by dou y minus dou by dou z. So here fz fy plus ay cap into dou by dou z minus dou by dou x. Here fx fz plus az cap into dou by dou x minus dou by dou y. So here fy and here fx. Okay, so always remember here, always remember for curl of f bar equal to 0, if curl of f bar is equal to 0, then what is the condition here? Then dou fz by dou y must be equal to what? Must be equal to dou fz by dou fy by dou z. So this condition, first condition, and second condition is dou fx by dou z must be equal to what? Dou fz by dou x. And then third condition is what here? Dou fy by dou x must be equal to what? Dou fx by dou y. So all these three conditions here, all the three conditions, all 1, 2 and 3 must be what? Must be satisfied, must be satisfied. Then only we can say the curl of the vector field is equal to 0. So whenever you want to check whether the curl is equal to 0 or not, you can follow this one here, you can follow this one. So make it as a note here, make it as a note. So it has to satisfy all these conditions here. If curl of f bar is equal to 0, then it has to satisfy all the three conditions, all the three conditions. So then only curl of the vector field will be equal to 0, right? Okay. Okay. So I hope it is crystal clear here. I hope it is crystal clear. So next here, next. So this is also previous gate question. This is also previous gate question here. This is also previous gate question. See here what they have given. If the vector function f bar is equal to they have given some function here. They have given some function. Okay. So 3y minus k1z ax cap, k2x minus 2z ay cap, minus of k3y minus z az cap. So this is the vector function they have given. So they are saying that this vector function is irrotational, That means what here? Irrotational means del cross f bar must be equal to 0. So this is what they are saying. So if del cross f bar is equal to 0, then the values of constants k1, k2 and k3. So you have to determine k1 value and you have to determine k2 value and you have to determine k3 value. So you have to determine these unknown values k1, k2 and k3 if the given vector function is irrotational. So that means del cross f bar is equal to what? Del cross f bar is equal to 0. Yes or no here? Yes or no? Okay. So just now we have seen the condition. Just now we have seen the condition for what? The condition for del cross f bar is equal to 0. Yes or no? So if del cross f bar is equal to 0, then what is the condition? It has to satisfy three conditions. What are they here? So differentiate the y component with respect to x. This must be equal to what? Differentiate x component with respect to y. Right. And what is the second condition? So differentiate the z component with respect to x. This must be equal to differentiate x component with respect to z. So this is second condition. And then third condition. So what is third condition here? So differentiate y component with respect to x. So already I have taken na. Okay. So you can take what is left out, that is differentiate z component with respect to y and differentiate y component with respect to z. Okay, so all these three conditions must be satisfied here. All these three conditions must be satisfied, right? Okay. Okay, so now I have told that always write the x component separately. So this is x component and this is nothing but what? This is nothing but y component, and I am including the minus sign here. I am including the minus sign. So this I can call it as z component, right? Okay, now check whether this condition is satisfied. This condition must be what? This condition must be satisfied, because they have given that curl of f bar is equal to what? Curl of f bar is equal to 0. That means they have given the function is irrotational. That means curl of f bar is equal to 0. So we know that if curl of f bar is equal to 0, then it has to satisfy all these three conditions, right? Okay, now here what you can do here is, now take y component here, take y component and differentiate with respect to x. So this is y component and differentiate with respect to x here. What you are going to get? You are going to get k2. Yes or no? You are going to get simply k2 on LHS side. Yes or no? This one will become k2. So now take x component and differentiate with respect to y. So this is x component. Now if you differentiate this with respect to y, what you are going to get? You are going to get 3. So k2 value is equal to what? K2 value is equal to 3. Yes or no? Okay. Next, take z component here. Take z component and differentiate with respect to what? With respect to x. So if you take z component, if you observe, z component is not a function of x, and hence dou fz by dou x will become what? Will become equal to 0. Will become equal to 0. So this is equal to, so dou fx by dou z. Take x component and differentiate this with respect to what? With respect to z. With respect to z. So what you are going to get? You are going to get simply k1 here, minus k1, or you can write it as simply k1, right? Okay, so k1 is equal to what? K1 is equal to 0. K1 is equal to 0. Next next, take z component and differentiate with respect to y. So here you are having minus here, so minus of, so differentiate it with respect to y, what you are going to get? Minus of k3. So this is equal to, now take y component and differentiate it with respect to z. So if you differentiate it with respect to z, you are going to get what? You are going to get minus 2. So here minus will get cancelled. Therefore k3 is equal to what? K3 is equal to 2. K3 is equal to 2, right? Okay, so that means the values of k1, the value of k1 is equal to 0, and the value of k2 is equal to 3, and the value of k3 is equal to what? Is equal to 2. Yes or no? Okay, so the answer is what here? They are asking k1, k2, k3 respectively. So k1 is equal to 0, k1 is equal to 0, k2 is equal to 3, and k3 is equal to 2. K3 is equal to 2. Okay, so that means option B is correct. Option B is correct. Yes or no here? Okay, is this clear here? Is this clear? Yes? Yes, is this clear here? Dev Sharma? Yes, okay. Okay, yeah. Next. Okay. So these are some of the few problems here I have taken from previous gate questions. Okay. Okay. And they have given some problems, they have given direct statements here, direct statements for divergence theorem and for Stokes theorem. So we have already studied about divergence theorem and Stokes theorem. They have given directly the statements. Okay, which one of the following is the correct representation of divergence theorem, which one of the following is correct representation of Stokes theorem. So like that they have given a direct questions here. So those things you can easily answer. Okay, so we have completed with this this we have completed the basic mathematics part here. We have completed the basic mathematics part. So we have completed basics of vectors, we have completed coordinate systems, and we have completed vector differential operator. In that we have completed gradient, divergence, curl, and also we have studied flux and circulation, and also we have studied divergence theorem and Stokes theorem, and also we have seen null identities. Okay, so with this the basic mathematics part is completed here. Okay, so next we will start the subject here. We will start the subject. So I am going to start electrostatics. I am going to start electrostatics here. Okay, so up till now we get familiar with the mathematics part that is needed for us to understand this subject. See, simple thing, if you understand, we are having Maxwell's equations here. Finally we are going to get 4 Maxwell's equations, yes or no? Okay, see, if I simply write, I am simply writing the Maxwell's equations here. So what are the Maxwell's equations you are going to have? The electric flux, I am simply writing here. Don't worry about this, we will study each and everything clearly later. Okay, just I am writing. So the electric flux that is leaving any closed surface is equal to triple integral rho v dv divided by epsilon. So this is first Maxwell's equation, that is Gauss law. Okay, so second Maxwell's equation I can write the closed surface integral b bar dot dA bar is equal to 0, and third one, the circulation of electric field, the circulation of electric field around any closed loop is equal to minus of double integral dou b by dou t dot dA bar. And fourth one, you can write the circulation of magnetic field, the circulation of H field around any closed loop, is equal to double integral jc bar plus dou d bar by dou t, or you can simply write, okay, dou d bar by dou t dot what, dot dA bar. Now these are nothing but what, these are nothing but 4 Maxwell's equations. See here, if you observe all these Maxwell's equations, how they are represented here, how they are represented, we know the flux leaving any closed surface, yes or no, the flux that is leaving any closed surface, how to represent the flux leaving any closed surface. So if you understand how to represent the flux leaving any closed surface and what do you mean by the flux leaving any closed surface, then you can easily understand what, then you can easily understand this Gauss law, yes or no. Okay, and also here you are having what, the magnetic flux that is leaving any closed surface is always equal to 0. That means we have represented what, we have represented in mathematical forms. All these laws we have represented in mathematical forms, yes or no, and we are familiar with this mathematical forms now. Okay, so you can easily understand the concept behind this, and we can easily understand the mathematical representations of this Maxwell's equations. Okay, so that's why I have spent this much of time on basics here, on basic mathematical part, right? Okay, see here we can this is circulation of electric field around any closed loop, and this is nothing but circulation of magnetic field around any closed loop. So we are familiar with all these expressions here, with mathematical expressions, yes or no? Okay, okay, yeah. Okay, so we will start the subject here. We will start the subject with electrostatics, right? Okay, see, so I will start the subject with one statement here. I will start the subject with one statement. So what is that statement? See here, all this electromagnetism is just because of an intrinsic property, that is possessed by the fundamental particles of an atom, that is possessed by the fundamental particles of an atom. So See here what I am saying. So I am saying that all this electromagnetism is just because of what here? Is just because of an intrinsic property. Is just because of an intrinsic property that is possessed by what? That is possessed by the fundamental particles. That is possessed by the fundamental particles of an atom. Fundamental particles of an atom. So here what do you mean by intrinsic property here? What do you mean by intrinsic property? Intrinsic property means it is unavoidable property here. It is unavoidable. So that means, see here, if you consider object here, if you consider any object, so what is the intrinsic property of any object here? Is nothing but its mass here. Is nothing but its mass. So you cannot take the object without its mass. Yes or no? So whenever you are taking an object, its intrinsic property, that is mass, will also comes along with it. So you cannot avoid mass and take the object. Yes or no? So it is unavoidable property of the object. That is nothing but mass. So that type of property we call it as what here? Intrinsic property. Intrinsic property. Okay. So all this electromagnetism is just because of this intrinsic property possessed by what? Possessed by fundamental particles of an atom. So what are the fundamental particles of an atom here? What are the fundamental particles of an atom? The fundamental particles of an atom are nothing but what? Electron and proton. Electron and proton. So these are the fundamental particles of an atom. So now what is the intrinsic property possessed by these fundamental particles here? What is the intrinsic property that is possessed by these fundamental particles? What is the intrinsic property of electron and proton? Is nothing but what? Is nothing but what here? Their intrinsic property is nothing but what? Is nothing but charge. Yes or no? So the intrinsic property possessed by these fundamental particles are now fundamental particles of an atom is nothing but what? Is nothing but charge. Okay, so all this electromagnetism is just because of this intrinsic property that is possessed by these fundamental particles of an atom. Okay, so that intrinsic property is nothing but what? Is nothing but charge. So that means this charge is responsible for all this what? For all this electromagnetism. This charge is responsible for all this electromagnetism. Why means, see here, if you consider a charge here, if you consider a stationary charge, so if you place a stationary charge, it is going to set up what? It is going to set up some static electric field in its vicinity. Yes or no? Now, if the same charge starts moving with uniform velocity here, if the charge starts moving with uniform velocity, then it is going to produce what? It is going to produce a steady current. It is going to produce a steady current. If you are having a steady current, it is going to set up what? It is going to set up a steady magnetic field. It is going to set up a steady magnetic field. Yes or no? So a stationary charge is the cause for what? Static electric field. If the charge moves with uniform velocity, it is the cause for what? It is the cause for the static magnetic field or steady magnetic field, right? Okay, now if the velocity of the charge changes with respect to time, or you can say if the charge is oscillating here, if the charge is oscillating, so a charge is oscillating means its velocity is changing with respect to time. Yes or no? So if the charge is oscillating means its velocity is changing with respect to time. So if the velocity is changing with respect to time means the current is also changing with respect to time. The current is also changing with respect to time. So if the current is changing with respect to time, we know that it is going to produce what? Current is going to produce the magnetic field. If the current is varying with respect to time means the magnetic field produced by that one will also varies with respect to time. So if the magnetic field varies with respect to time, we are going to study that a time varying magnetic field is going to produce a time varying electric field, and this time varying electric field in turn is going to produce a time varying magnetic field. So one is going to produce the other, and they are going to travel through space, which we call them as what here? Electromagnetic waves. Electromagnetic waves. So that means this oscillating charge is producing what here? Is producing electromagnetic waves. Yes or no? So stationary charge is producing static electric field. So if the charge is moving with uniform velocity, it is producing steady magnetic field. If the charge is oscillating with respect to time, then it is producing electromagnetic waves. So all this static electric field, static magnetic field, and electromagnetic waves. What is the cause? Cause is nothing but what? Charge or not? Yes or no? Okay. So for all this electromagnetism, what is the cause here? The cause is nothing but charge. So this is responsible for all this electromagnetism, right? Okay, so that's what this statement mean here. That's what this statement mean, right? Okay, Okay, yeah. So now see here, if suppose, so okay sir, charge is responsible for all this electromagnetism. Okay, fine. Now if you consider some material here, if you consider some material, some neutral material, if you consider some neutral material, right? So if you consider neutral material, so inside that neutral material, you are going to have huge number of protons. Yes or no? That means huge number of positive charge carriers, and also it is going to have huge number of electrons. That means huge number of negative charge carriers. Okay, so even though this material consists of both positive charge carriers as well as what, negative charge carriers, but we cannot see the effect of what, but we cannot see the effect of charge. Yes or no here? Even though the material is having huge number of protons and huge number of electrons, we cannot see the effect of what? We cannot see the effect of charge. Why here? Why means here the number of positive charge carriers is in balance with what? Number of negative charge carriers. That is, number of protons will be equivalent to what? Number of electrons. So whenever these charges are in balance, we cannot see the effect of what? We cannot see the effect of charge, because the effect of positive charge will get nullified by what here? The effect of negative charge. Okay, that's why we are not going to see any effect of what here? Any effect of charge. Understood? Now if you want to see the effect of charge here, if you want to see the effect of charge, then what you have to do? You have to create a charged material. You have to create a charged material. So how we can create a charged material here? How we can create a charged material? By creating what? By creating charge imbalance. Yes or no here? So if we create charge imbalance, then we can create what? Charged material. So how we can create this charge imbalance here? How we can create this charge imbalance? See, if you are having a material, if you are having a neutral material, okay, so if you take the electrons out of that material, then in that material the positive charge carriers will become dominant over the number of negative charge carriers, and hence that material is going to behave as what? Positively charged material. Yes or no? In the same manner, if you try to supply the electrons, to a material, then what will happen here? What will happen? The number of negative charge carriers will become more when compared to positive charge carriers, and hence here the negative charge is going to get dominant over the positive charge, and hence the material is going to behave as what? Negatively charged material. Yes or no? Okay, so in this manner we can create what here? We can create charged materials. So once we create a charged material or charged particle, okay, it is observed that these charged particles are exerting the forces on one another. It is observed that these charged particles are exerting the forces on one another. Okay, so if like charges, if you are having like charges, it is observed that they are repelling each other. If they are unlike charges, it is observed that they are attracting each other. So that means the final conclusion is, if you are having any charged particles, so those charged particles are exerting the forces on one another. If they are like charges, they are repelling each other. If they are of opposite charges, they are attracting each other. Okay, so now we want to determine the force between those charge carriers, Okay, so who will help us to determine the force between any two charges here? Who will help us to determine the force between any two charged particles? Who will help us here? He is nothing but what? Coulomb or not? Yes or no? So Coulomb will help us to determine what? To determine the force between what? The force between any two point charges. So we know that the charged particles are exerting the forces on one another. Now if you want to determine the force between any two point charges, who will help us here? Coulomb will help us to determine the force between any two point charges. Yes or no? So that is given by what? That is given by Coulomb's law. Yes or no? That is given by Coulomb's law. Right? Okay. So I hope you know this Coulomb's law very well here. Whenever you are having 2 point charges separated by some distance r, okay, so then the force between those point charges is directly proportional to product of charges and inversely proportional to square of the distance between them. So I hope all these things you know already, right? Okay, yeah. So we will start this Coulomb's law and we will study about the force between 2 point charges, how to calculate the force between 2 point charges, how to write the magnitude, how to write the direction. All these things we will see in the next session here. So in the next session I will briefly discuss about this Coulomb's law. Next I am going to start with electric field here. Next I will start with electric field, and then we will start Gauss law here. Then we will start Gauss law. Okay, so in the tomorrow session I will just briefly explain about this Coulomb's law, and I will explain how to determine the magnitude and direction. Okay, so calculating magnitude is very simple, but while calculating directions, generally the students will get confused here. Okay, so I am going to explain how to calculate the magnitude and also how to write the direction. Both the things we will discuss. Okay, so once we complete the Coulomb's law, then we will define about electric field. So once we understand what do you mean by electric field, then we will go for what? Then we will go for Gauss law. Okay. So with this I am winding up the session for today. So tomorrow's class, we will continue from here. We will continue with Coulomb's law, right? Okay. Yes, Dev Sharma, F is equal to Q1 Q2 by R square, K into, yes, K is some proportionality constant, right? So we will study everything here. What is that proportionality constant, on what factors this force is going to depend. So all these things we are going to study here in the next session. Okay. So I hope up till now, I hope it is crystal clear here. Up till now, right? Yes or no here? Is it clear up till now? Yes? Yes, Dev Sharma, is it clear? Yes, is this class on same time tomorrow? Yes, daily it is going to be at 4 p.m. here. Daily this session will be at 4 p.m. Okay, so daily EMT session will be at 4 p.m. here, 4 p.m. right? Okay, so I hope you have understood up till now clearly. So I hope it is crystal clear whatever we have discussed today's session. Okay, I hope it is crystal clear. So we will meet exactly at 4 p.m. in the tomorrow's session here. So until then, take care, bye bye.